500,000 atoms wide. That's crazy how small atoms are. But a molecule is a combination. Oh my goodness. So check out what I have here. I have sugar, okay? This is ball and stick. Molecules. Redeem Academy. Yo, what is up, Science Squirrels? Johnny here with Redeem Academy. I am here to help you get the most out of your education while giving God the glory he deserves. Hey, we are on lesson 2 of our chemistry unit. Today's lesson is all about molecules. In today's lesson, I'm going to be going over 4 things. I'm going to be reviewing atoms and elements. I'm going to be teaching you all about molecules and what they are. I'm going to teach you how to count atoms and molecules with chemical notation and how that works in a chemical formula. And I'm going to go over element symbols, make sure you know how to read element symbols and understand where they came from, how to read them, how to write them. All right, big question today. If God made atoms join together and become more than they are by themselves, what might that tell us about how he designed people? All right, and we need to give a shout out to our sponsor today, sugar. Oh, that sweet nectar from heaven. Don't you just want to lick it when you see it? Is that not what you picture in your mind when I say sugar? You know, 3 out of 4 sugar molecules are subscribed to Redeem Academy. And they say you should be too. Think of all the great things sugar's done for you in your life. Sugar high, cavities, sugar low. But if you don't want to develop a dad bod and type 2 diabetes, I suggest you go to redeemacademy.org. Get a notebook to follow along if you don't already have one. Hey, and maybe slow down on the candy corn, okay? Just tone it down a bit, trust me. You'll thank me later. All right, like I said, we're gonna start off with a review of atoms and elements. Let's hit the notes. The microscopic marbles that make everything up are called atoms. I've got a great video about this.
What is an atom, and how do we know? Atoms are the fundamental building blocks of chemistry. Just like baked goods are made of a collection of different types of ingredients, matter itself is made of a collection of different types of atoms. Scientists have discovered 118 kinds of atoms, which we call elements. You can find them laid out on a chart called the periodic table. All things from the screen this video is displayed on to the eyeballs with which you're watching it are made of atoms, but a single atom is so small it is impossible to see with the naked eye.
I think I've already taught you that. Tiny microscopic marbles, too small to see, make up everything. Did you catch this little detail? A human hair is roughly 500,000 times wider than an atom. That means one hair has about 500,000 atoms in it. The thickness of a periodic table, 500,000 atoms wide. That's crazy how small atoms are. Did you know scientists have been able to see them in a sense? Check this out.
Are far too small to be seen with normal light. The wavelength of light is just too great. This means that normal microscopes cannot see atoms.
All right, did you catch that? So you can't see atoms because they're smaller than the wavelength of light. So you can't just use a microscope to see them, but scientists have developed a new technology in the 80s, which is a long time ago. That's when I was born, 1984. They developed them in the 80s, this technology, to see atoms under the microscope.
In the 70s, a group of engineers led by Gerd Bennig and Heinrich Rohrer began working on what they called the scanning tunneling microscope, a microscope they hoped would let us take undistorted images of many different types of atoms. It uses a process called electron tunneling to scan and essentially feel the surface of the sample, much like you can feel around in the dark to get a picture of your surroundings. This is an actual scan of silicon atoms forming the surface of a crystal.
So atoms are so small that light waves are actually bigger than atoms. And so wavelengths of light are what we perceive as color. So atoms don't have color. So like I've got this model of sugar today, I'm going to show you a little later, and we've got red, black, and white atoms. Well, actually, we just assign colors to atoms to remember, help us remember, but really atoms have no color because they're so small, they're smaller than the wavelengths of color. So in this diagram, they add color based on the feelings of the tip of that little thing, but really they've just felt the shapes of the atoms and built a picture and assigned colors to the shapes.
Later work by Dr. Wilson Ho improved the technique and cleaned up the presentation of data.
A little nicer picture.
Well-
Now, later on, I think maybe this picture I was talking about is from the 80s. Scientists used the scanning tunneling microscope to actually pick up individual atoms and set them down on purpose. And they were able to set them down, and they put down the name of their company. Maybe you could guess what company it was. And here's another picture of the same idea. They took, I don't know if they took two different pictures or if they used different, I don't know. But they used, I want to say it was nickel that was the surface, so that's a metal. And then they used xenon, which is a gas. And so they had to get this extremely cold. They got it like within 2 degrees of absolute zero, where there's no motion to the particles anymore. And so it's like, I want to say it's like negative 279 Kelvin, which is a different way than Celsius or Fahrenheit. And so it would have been like negative 277 Kelvin when they set all these xenon atoms down on nickel, and they got them motionless and felt them with their little feeler device to feel if they're in the right spot. Now, they don't have this technology perfected yet where they can mass produce things that they're setting atoms down with.
That sounds awesome.
But someday they may be able to build like quantum computer chips with this technology for quantum computers, if you've heard of that crazy like science fiction sounding stuff. But right now, they do use mass production to make like the chips for our cell phones, and they print, or they don't print, but they lay down. A guy I went to high school with became an electrical engineer, and he got to work in this technology where they print or they lay down 5 atoms thick at a time to build computer chips. And these are the computer chips that are in our cell phones that run the CPU, the computer processing unit, and the GPU, which is the graphics processing unit. My cell phone, I want to say it has either 64 or 128 gigs of storage, and that's in the hard drive. And when I was in high school, 2002, long ago, back when dinosaurs roamed the earth, I built my first computer, and it had 40 gig hard drive, and the hard drive was like a box this big, about the size of like a sandwich or something. And now you can get, with that kind of technology where they just print individual layers of atoms, like 5 atoms thick, you can get entire hard drives that are just really small because they've gotten so good at laying down thin layers of atoms like that.
Tecnologia! Tecnologia!
All right, so anyway, atoms are those tiny little marbles that make up everything, and a totally pure substance of the same atoms is called an element. So if you had a thin layer of silicon, which is what's in most computer chips, you'd have the element silicon. If you had a thin layer of copper, you'd have the element copper. Now, one thing that is not an element that you might think would be an element is water. Let's go look at water really quick. All right, so sometimes I show you guys videos and I speed them up. I rarely slow them down, but I've actually slowed this one down. These are, I don't know, 300 or 400 water molecules in a simulation, and it's a simulation of water freezing. And so right now at the top of the simulation, you can see water and it's frozen. Okay, so this section up here represents frozen water. It's become a solid, it's bonded together. But then all this water down here, I'm going to go with green. All this water down here is liquid water. Okay, and so as this video progresses, the water is freezing and it's all becoming frozen water. Now, what you should notice about these water molecules is that they're not made out of a single atom, but they're made out of multiple atoms. I'm going to show you another video of water. Okay, so water is H2O. 2 hydrogens, 1 oxygen. Now watch what happens when I play this video. We see the H's and the O move, and we see that water has 2 hydrogens that are white, 1 oxygen that's red, and then they show it to you in 2 different styles. And I'm just going to let this thing play again. So that's called the ball and stick model right there. Really creative name, as it has balls and sticks. And that right there is called the space filling model. Just watch it through one more time. Okay, ball and stick model. The white ones are hydrogen, the red one's oxygen, and then boom, space filling model. And so the space filling model is what water actually looks like. If we had that funny scanning tunneling microscope to feel it, that's what it would look like when we would feel it with the scanning tunneling microscope. It'd have 2 hydrogens on the bottom end there and 1 on the top. So this brings us to the idea of a molecule. A molecule is not a single atom, but a molecule is a combination. Oh my goodness, how did you do that magic trick, Johnny? You're going to have to play it back to catch that one. A molecule is when you combine two atoms together. So in simple terms, a combination of two or more atoms is a molecule. All right, so I have a little demonstration for you. Is the song I'm playing made out of atoms, one note, one string, or is the song I'm playing for you made out of molecules, all the notes together? I would like to start off with a song that really means a lot to me. Hit Me Baby One More Time by Britney Spears. Just kidding. I would never. Atoms. Okay, how about... molecules. Okay, molecule is when you take multiple atoms, multiple strings, and you play them together all at once. Okay, one more. We gotta go to drop D for this. This is Heaven Let Your Light Shine Down. I once played this in an assembly at our school while a gorilla ran around the whole assembly. It was a great moment. Both. It's got a little bit of both just to confuse you. All right, there's a lot of cool things that could come out of that idea that one note, one string is an atom, but you combine them and you can turn it into something totally new and make a molecule. And so you can take a single atom, throw it in with some more atoms, and voila! Instead of having a note that's a G, you can have a note that's an E. And if you play piano, same concept. Now, same channel has a great video, What is a Molecule? So we're going to watch a fair amount of this one as well.
What is a molecule? Though textbook definitions of the word molecule can sometimes be a bit complicated, a molecule can be loosely thought of as a group of atoms stuck together, usually through chemical bonds. Here we see a single hydrogen atom traveling through the cosmos. It's made of one positively charged proton in its nucleus and one negatively charged electron. If our lone hydrogen atom happens to pass close enough to another lone hydrogen atom, their electrons, which are attracted like magnets to protons, can pull the atoms toward each other until they collide and stick together. The two atoms now share each other's electrons in what is called a covalent chemical bond. What were once two individual hydrogen atoms have now formed a single hydrogen molecule.
Isn't that weird? So that is two hydrogen atoms become one hydrogen molecule. Strange. It would be like if I play 3 different notes on my guitar, or 2 different notes on my guitar, that are both a D, and I put them together, now they're a D chord. Even though it's a D and D, together, they're not a D atom anymore, or not just a D note, they're a D chord. In the same way, 2 hydrogen atoms come together and now they're a hydrogen molecule.
This bond is not permanent. With enough heat or due to interactions with other molecules, the hydrogen atoms will readily separate once more. Different types of atoms can form different numbers of chemical bonds. A hydrogen atom can only form one covalent bond at a time. If a third hydrogen atom were to collide with a hydrogen molecule, it would simply bounce off, or if it hits hard enough or in just the right place, it can trade spots with one of the existing atoms.
Now that's another really good principle. The thing that's needed for bonds, for molecules to form, is collision. They only connect with each other when they run into each other, and they have to run into each other with enough force and speed to separate the other one.
An oxygen atom can typically form 2 bonds.
Hey, we just saw him. What's his name? Water.
A carbon atom can make 4.
That's called methane. Comes out of cows' butts.
An argon atom won't usually bond with anything.
Nothing, just like neon. Won't bond with anybody. All the guys in the last column on the periodic table will not form bonds. They're called the noble gases.
Even though possible bond numbers per atom are pretty small, huge molecules can form if bonds happen to be properly arranged.
Check this
For
out.
example, even though hydrogen can only form 1 bond, a standard water molecule is always made of 3 atoms. This is possible because oxygen, which can form 2 bonds, forms just 1 bond with each hydrogen atom.
Beautiful.
A single molecule of the sugar known as glucose is made of
Glucose, sugar. Today's sponsor. Wonderful.
24 atoms, a special arrangement of carbons, hydrogens, and oxygens. A typical fatty acid in the human body may vary
Fatty
in length.
acid. That's butter.
This one here is made
Take a
of
bite.
38 atoms. And finally, a single protein, depending on the type, can contain over 500,000 atoms all covalently bound together. The molecular models that I've been showing you here so far are what we call space-filling models. They show us roughly what the outside of each atom's electron cloud looks like, and different types of atoms have been assigned different colors. When we look at real molecules with a scanning tunneling microscope, they look pretty similar to these space-filling models, but the atoms are not color-coded and their edges are fuzzy. That blur is partly due to the microscope's limitations, and partly because atoms actually do have soft boundaries.
Remember what the scanning tunneling microscope is? Is the thing I just showed you with the needle and they feel around and actually feel the shape of the atoms? He just showed you another picture of that.
When looking at complex molecules, space-filling models, and especially actual images of real molecules, can be a bit confusing to look at. Which atoms are bound together, which atoms are just close to one another. For this reason, chemists sometimes use what are called ball and stick models.
Yes.
These highlight the bonds between atoms, the skeleton of a molecule, instead of showing each atom's outside surface.
Perfect.
And
So check out what I have here. I have sugar, okay? This is ball and stick. Now he showed you sugar, space filling. See the difference? All right. I think we've got enough now to get into our notes. All right, so one of the main things I'm actually wanting to teach you today is how to read a simple chemical formula, okay? So I'm going to put a little bracket over the top of this guy, and I'm going to write the word chemical formula right here. So this is the chemical formula of 3 water molecules. Now this big 3 in the front is called a coefficient. I'm actually going to put that down there. And this little 2 right here is called a subscript. Now, in order to understand what the 3 and the 2 mean, we're going to draw a picture of water over here. So you just got water's space-filling model. So in the space-filling model, we have 3 oxygen atoms that represent 3 different water molecules. Might not have left myself quite enough room on that one. And I'm going to wrap these guys up with 3 hydrogens on top. So the way water looks, a lot of people think water looks like a teddy bear, or people think water looks like Mickey Mouse. It's got this shape where it's bent, and the hydrogens are bent to the top of the molecule, and the oxygen is down at the bottom. The oxygen is red, the hydrogens are white. Now, that is the space-filling model where we draw 3-dimensionally like what it would really look like. Now, I happen to have toys of what the ball and stick models would look like. So this would be the ball and stick model for 3 water molecules. So now I'm going to draw this one. It's going to have oxygen molecule in the middle that's a little bigger than the hydrogen molecules. Hydrogen is the smallest element on the periodic table because it only has 1 proton. So nothing is smaller than hydrogen. And hydrogen is always drawn as white. It's not that hydrogen is actually white. It's just that's the way it always gets drawn. And oxygen always gets drawn as red. It's not like oxygen's actually red. There are no colors down that small. It's just the way it gets drawn. And so this is 3 water molecules. Each one is a separate entity, but when we have a big 3 right here, it means there are 3 of them. So that's what the big 3 in the front means. That's what the coefficient means. And the little 2 applies to the hydrogens because on each molecule there are 2 hydrogens. So the 2 means 2 hydrogens, and the O means 1 oxygen, and the big 3 means there are 3 water molecules. So you're going to see this in your workbook. I'm going to say, how many hydrogens? Well, there's 2, but there's 3 molecules. The trick, whenever you do this, is just 3 times 2. 3 times 2 is 6. Okay? Oh, there's an oxygen. Now, we could draw a 1 there, but that would be redundant. And so we just say 3 times 1. There's 3 oxygens, 3. Okay? Now, I like to ask the question, well, how many atoms are there? Well, there's 6 hydrogens, and there's 3 oxygens. So there's a total of 9 atoms, right? Look at this. Okay, if I were to count all the marbles, how many marbles are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 marbles. Okay, and then I like to ask the question, well, how many molecules are there? The big 3 in front tells you there are 3 separate molecules. 1, 2, 3 molecules. Okay, and so I've got problems in your workbook that are asking these questions. Now, sodium chloride, table salt, that good stuff that we like to eat. Same idea. Sodium chloride, I'm going to use green and gray, but unfortunately, I only had 2 in my chemistry set, so I can't even draw 4 of them, or I can't even show you 4 of them. I can only show you 2 of them. Okay, but imagine that there's 4 of those right there. Okay, because the big 4 in front says there's 4. Now that big number in front, let's go back to the notes real quick. The big number in front is called the coefficient, and the little number after and below is called the subscript. Okay? The way that we draw it that accurately presents the real shape of the molecule, that's called the space-filling model. And then the way that we draw it that actually represents the bond angles, so space-filling does too, but it's just hard to see them, but this represents perfectly the angle of how the bonds attach. It's called the ball and stick model. Okay? All right, now we're back over here, and we're at sodium chloride. Now, one important detail that I've left out here is look at sodium's name, Na. Where did that come from? That doesn't say sodium. All right, so I Googled, where does sodium get its symbol from? I've never actually looked this up. I just heard it was Latin usually, and I've never looked up sodium in particular. I know iron, Fe, gets it from ferrous. Okay, that might be the only one I've ever looked up. So I looked up sodium today, and it's from the Neo-Latin name natrium. Okay, never heard of that. Okay, and so if you spoke Latin, natron is probably a word that means it's some mineral that people knew about. Natron was a mineral. All right, had no idea. This is kind of cool Christian history. Christians the Bible was mostly written in Greek. I don't know if I've ever told you guys about this thing that sits on my desk, but this is one of the earliest fragments of the New Testament, maybe the earliest fragment of the New Testament. It's called the John Rylands fragment. It's in a museum, the real one, mine's a replica. It's in a museum, I think in England. It's a little section of the Gospel of John, I want to say chapter 17, 18. It's the part where Pilate says to Jesus, "What is truth?" And he's like scoffing. But the cool thing is it's from 110 AD, 120 AD, something like that. So literally it's a copy of the Gospel of John that was written in 90, and they already found a copy of the manuscript from 120. So just shows how early the Bible was written. It was of course written, when Jesus was alive and when his disciples, John was still alive in 90 AD. But then it was just getting sent out. And Christianity's true. Christianity really happened. So anyway, but this is in Greek. The markings, if I could read Greek, this would say what is truth on it. When Jesus was alive, people spoke Greek. The Bible's written in Greek. We have lots of the early manuscripts of the Bible still in Greek. But by I want to say 500, 600 AD, people aren't speaking Greek anymore, and they're not speaking Hebrew. Even the New Testament, or the Old Testament, was translated into Greek. So they're speaking Latin. So the Bible got translated into Latin, and for 1,000 years, people were speaking or reading the Bible in Latin. And so that actually transferred into the scientific community because the early scientific community was Christian people, and they learned Latin just to read the Bible in Latin because people hadn't gotten like, oh, we speak English now, translate the Bible to English. So the Latin and the Greek words made it into medicine, and they made it into chemistry. And so biology and chemistry have a lot of Greek and Latin words because the world was Christian when it invented chemistry and biology. And so we go back to, why is sodium Na? Sodium is Na because it was the Latin word that meant sodium, basically. And a lot of the words on the periodic table, if they don't have their normal, like carbon is C, sulfur is S, oxygen is O, if they don't have their normal letter, they have their Latin letters. And that is just a testament to the fact that science was started by Christians. Now there's one other thing about an element symbol. There's 118 elements. There's only 26 letters in the alphabet. So a lot of elements have to have 2 letters. And when you do that, the second letter can't be capitalized, because if you have like carbon and oxygen, is that cobalt? No, because cobalt is big C, little o. Carbon and oxygen, like carbon dioxide, is big C, big O. So the second letter in any element that is just still for the one element, like sodium, Na, the A has to be a little a. Okay, flip over here. Like I mentioned earlier, elements usually get their weird names from Latin. There's probably an exception to that. The solution to the fact that there are 118 elements, only 26 letters, is you got to use 2 letters on a lot of them. The first letter always needs to be a capital, and the second letter always needs to be lowercase. Now, you may have noticed that I always write in uppercase, but if I write sodium, it comes out in lowercase. Or if I write iron, it comes out in lowercase, because it's got to be lowercase for those kind of things. Johnny can write in lowercase? It's true. All right, that was quite a spiel to explain that sodium is Na.
It's Latin.
All right, so now we have a 4, an Na, and a Cl. Let's draw NaCl real quick. The actual right color for sodium is actually purple. So we're going to do a purple and then a smaller green. Oh man, you know what I just noticed? This is a 4, not a 3. I need to add 1 more on each of these. All right, so now that everything makes sense, 4 NAs, 4 times 1, it's like there's a 1 here, okay? And it's like there's a 1 here, but because, you already wrote Na, you already wrote Cl, you don't have to write the 1s, but I wrote them there just so you know they're there, but pretend they're not there now. 4 times 1 equals 4. 4 times 1 equals 4. So there's 4 sodiums, 4 of those purple things. Okay, how many atoms are there total? In this, there's 4 purples, and then there's 4 greens. So 4 plus 4 is 8. And then how many molecules are there? Each one of these units is a separate molecule, so there's 4. All right, that brings us to the monster who I've been flashing around all day, who causes cavities but brings us great joy. All right, so this legend is called a sugar molecule. You can count them: 1, 2, 3, 4, 5, 6 black atoms. Black is carbon. And then you can count the red ones: 1, 2, 3, 4, 5, 6 red atoms. And then there's 12 of the white ones. Those are hydrogens. So we got 6 carbons, 6 oxygens, and 12 hydrogens. All right, so here's what we're going for in drawing the space-filling model of sugar.
Okay, I like it, Picasso.
So beautiful. I'm so proud of a sugar space-filling model. So proud. It actually kind of looks like a Teletubby that got ran over by a car. I think that's what I would call that. All right, now for the ball and stick model. This one won't be as hard. Okay, now I have zoomed way in for you for the ball and stick model. I actually have this one memorized. All right, now to wrap this bad boy up, C6H12O6, that's the chemical formula of sugar. C times 6, or just 1 carbon of 6, means there are 6 carbons. And a 12 there means there are 12 hydrogens. a 6 there means there are 6 oxygens. Since there is no coefficient in front, it's like 1 times 6, 1 times 12, 1 times 6. And then as far as how many atoms are there, well, it's 6 plus 12 plus 6. So there are 24 atoms in that molecule. And there's a big 1 in front here, so it's like there is 1 molecule. That is this guy, our 1 molecule of sugar. All right, let's wrap this thing up, bring it in for a landing. If God made atoms to join together and become more than they are by themselves, most of the cool things God made on this earth, all the living creatures, probably most rocks even, they're not just an individual atom, they're a combination of atoms. If he did that with the atoms, what might that tell us about how he designed people? You, friend, were not made to be alone. God looks at Adam in the garden and he says, it's not good for man to be alone. People are made to be in community. And God created man to go with woman in community, in marriage. But also God has now made this glorious thing called the church. And I think if Paul the Apostle was a science teacher, although honestly, his metaphor is very science teacher. I used to teach anatomy. It's a great metaphor. We are the body of Christ. Okay, not everyone's the hands, not everyone's the eyes, but maybe if he were a chemistry teacher, if Paul the Apostle were a chemistry teacher, he'd say, hey, not everybody gets to be carbon. Carbon is the backbone of most biological molecules, but not everybody gets to be carbon. Somebody needs to be sodium, you know, just the salt that we eat. Somebody needs to be potassium, you know, you just need a little bit of potassium from those bananas. Somebody needs to be sulfur. Sulfur is what makes your farts stink. But sulfur is also essential for proteins. You got to have sulfur for proteins. So as human beings, we need each other. We need to be in community with each other in a church. And so God designed us to be a part of each other's lives, just like he designed atoms to go together and make molecules. He made Christians to go together and make the church. Hope this lesson blessed you, was interesting, helped develop a better understanding of atoms and molecules for you. When you do the workbook on this one, you need to probably go watch the YouTube video where I explain how to do the workbook on this one. And probably that's true for most of the chemistry unit. Have a great day. Peace out, Brown Trout.